Our next speaker is Dr. Bissan Ghaddar, the fourth generation. Bissan is an associate professor of management sciences at the Ivy School of Business, and her research focused mainly on developing efficient algorithms to solve the common to encounter but hard to analyze and deal with non-convex optimization problems. Her work has applications in energy, transportation, and telecommunication networks. Bissan received her PhD in operation research from the University of Waterloo. Before joining the Ivy School of Business, Bissan was an assistant professor at the Department of Management Science at the University of Waterloo. But her work profile is actually more diverse. She worked at IBM Research and the Center of Operation Research and Analysis, Department of National Defense, Canada. Her work had been published in many prestigious journals, SOCP, math programming, and many others. And her research has received funding on the national and international level. Bissan, the floor is yours.
Thank you so much, Shwala, and thank you for you and Henry for the invitation. And actually, it's really a pleasure and an honor to be presenting in the same session as Miguel, my PhD supervisor. I know it's been a long time since I graduated, but it's really always nice to see you, Miguel. So in terms of today's talk, it really flows nicely with what Miguel has been talking about. I'll start sharing first my screen. Can you see my screen? Oh, okay, good. So I'll be presenting working on ACOPF or alternate current optimal power flow problem, but from a polynomial optimization perspective. And Miguel has introduced the problem really nicely. I will be showing you again the problem formulation and how we tackle it from a polynomial optimization point of view. But I'll also talk about the uncertainty component that Miguel touched on. So I'll be showing you first conic relaxations for this problem based on SDP and SOCP, as well as talking a bit about the chordal extensions and how we exploit sparsity in the problem. But then the next part of my talk will be focusing on the uncertainty and how we can integrate renewable uncertainty to solve small to medium scale AC optimal power flow problems. And so with that, I would like to start by a brief introduction on polynomial optimization and the framework that we'll be looking at from a polynomial optimization point of view. So what we're talking about is a general polynomial optimization problem of the form minimizing f of x subject to a set of inequalities gi of x. Here we have the degree of the polynomial optimization problem we considered to be d. And then we know that since polynomial optimization capture a large class of combinatorial optimization problems as well non-convex quadratic problems, they are generally NP hard to solve. What has been done in practice is several things in terms of developing conic relaxations for these problems. And mainly there's the relaxations that are based on sum of squares decompositions that have been shown to be very tight. Theoretically, and these are based on a sequence of semi-definite based relaxations that under some mild conditions would converge to the optimal solution of the original problem. Of course, theoretically, these problems are nice and they converge. However, computationally, they are very expensive to apply in practice, and especially for practical problems that we're looking at, the optimal power flow problems. So in terms of focus, we would like to develop new approaches for solving general polynomial optimization problems, and then particularly apply these problems to practical applications, and mostly today focusing on the energy side. We've also been able to apply them successfully to water networks and networks that exhibit a similar type of structure that we'll be talking about today. So let's look at the problem again. So we have the following polynomial optimization problem. In terms of the dual of this problem, we can write the problem in the following dual format, where we maximize lambda, where f of x minus lambda is non-negative over this region S, where S is just denotes the set of inequalities, which is the feasible region that is specifying the polynomial optimization problem. So we'd like to maximize lambda as much as possible, such that this constraint remains non-negative over the feasible set S. We can replace this condition by the following cone. So now we replace it by PD of S, and the cone PD of S is the cone of non-negative polynomials that are of degree at most D, which is the degree of the polynomial optimization problem, that are non-negative over S. Of course, replacing this condition by this cone PD of S is still difficult, so solving over this cone is NP hard just because of the complexity that's still embedded there. And for some D's and S's, we can have like some particular examples. For example, when D is 2, the degree is 2, and S is just like H, which is the vertices of the hypercube. This is a quadratic problem, and it's also difficult to solve. So for particular D's and S's, we have some classical problems, and these classical problems are even hard to solve. So in general, as I said, solving over this condition is NP hard. So what we would try to do is replace this cone PD of S by another cone M. And this cone M will be a subset of PD of S. And we would like to find a cone M such that it's a nice trade-off between the quality of the bounds, because this problem will give you a relaxation of the original problem. And this means that it will give you a lower bound on the original problem. And we want to have some trade-off between the quality of this lower bound as well as the computational time that is required to solve over this cone M. So in terms of these trade-offs, we would like a cone M that's reasonable enough such that we can have good quality bounds and at the same time tractable to solve. And the work of Lasserre and Perello in the year 2000 really started this hierarchies of semi-definite-based relaxation, or SOS-based relaxation, that leads to semi-definite-based hierarchies, where they use this cone K of R, where K is the cone defined as follows here, and R is the degree of the sum of squares that are represented in the following way. This R, like the lowest value that it can take is D, which is the degree of the polynomial optimization problem, but then R can increase to take higher values to lead to meta relaxations, but at the same time, these relaxations will be much more expensive to solve. So replacing this cone KR with the following form, where we have this cone here, K of R is sum of squares of degree at most R, and then for each inequality gi of x, we will use another cone, which is sum of squares of degree, r minus the degree of the inequality. Now this problem, once you write it in a proper format in terms of equating monomials on the left-hand side and the right-hand side, as we'll be seeing in a second, would lead to a STP problem, because we know that sum of squares can be recasted as STP programs. Now, why is this a relaxation on the original problem? Because we know that every sum of squares is non-negative, is a non-negative polynomial, which means that every sum of squares here can be a non-negative polynomial, but not every non-negative polynomial is a sum of squares. So this is why it's a relaxation, and as you increase R in terms of the degree, then we have, under some mild condition, a proof of convergence to the optimal solution of the original problem. However, it's increasing the sizes of the STP matrices because it's increasing the degree of the sum of squares polynomials here, which would lead to very large scale type of STPs. And this is exponentially becomes very difficult to solve in practice, even for very small number of variables and very small degree. So how can we cast that as an STP? We will be using the following. So we have f of x minus lambda. We will substitute that here, like we will have a polynomial as 0 of x, and this is a polynomial that is sum of squares of degree at most r, and here we have polynomials that are si of x of a lower degree, r minus the degree of g. Like now these polynomials can be written in matrix format, like x as x transpose, and this S, big S matrix can be needs to have an STP condition. So this will lead to the STP matrix conditions, and then we'll end up with a linear matrix system of inequalities. And this would have a lower bound on the problem, which under as well some condition, as I said, some conditions would converge to the optimal solution. And the number of SDP matrices depends on the number of inequalities, but the biggest size of the SDP matrix is the size of this S0 of x related to S0 of x, which is n plus r choose r. So that's the size of the S0. The sizes of these are dependent on the degree of G, but they are relatively comparable as well. So in terms of challenge, we have the following challenge. What we want to do is try to find some other approach in order to come up with algebraic geometric representations that will be producing hierarchies of approximations to the problem, however, at a cheaper level. So the first step that we looked at is try to look at problems that are of higher degree and try to reduce the problem degree to start with. So if the problem, for example, is not a quadratic problem, is there a way or is it possible to transform it into a quadratic problem? And how much does that involve in terms of the complexity or add in terms of the complexity? Try to exploit the sparsity characteristic of the problem, because a lot of the practical applications that we're looking at, for example, the energy and the water networks that I've worked on, can be represented as sparse graphs. And as we've seen in Miguel's talk, also exploiting sparsity has a big impact in terms of reducing the number, in terms of the computation time of these instances. And then also one main thing that we'll be looking at is, can we find some cheaper relaxations? So instead of using SDP and sum of squares type of relaxation, are there any cheaper relaxation that we can substitute these? So these are the things that we'll be looking at. And the first step is looking at the sparsity or exploiting the sparsity. And this really feeds into the matrix completion approach that allows us to exploit sparsity in the SDP relaxation. From a polynomial optimization perspective, Wacky and co-authors in 2006, they proposed the following hierarchy of SDP relaxations to polynomial optimization problems. And you can see now here, instead of having one single S0 of x, we are now replacing this S0 of x by a sum of multiple S0k of x. And these would lead to smaller SDP matrices. Of course, we will have multiple of them, but they are much smaller in terms of size. And the same thing here for the Si of x that are being multiplied by Gi of x, we will be ending up, instead of one SDP matrix, by a multiple of SDP matrices. And these SDP matrices are generated exactly as Miguel described in his previous talk, in terms of looking at the cliques and trying to come up with these matrices that are shrinking, much lower in terms of size. So here, Si of k is sum of squares, but it's supported on Ck, which is the set of maximal cliques of a chordal extension of the correlative sparsity pattern of the graph. And here we still have the condition that as R grows in terms of number, so as we increase the level of the hierarchy, we still have convergence to the original solution of the original problem. Now, it might not be the same level as the non-sparse hierarchy proposed by Lasserre and Perello, but we have a proof of convergence. And here the sizes of the SDP matrices are much smaller in size, and they depend on the size of Ck. So it's the size of Ck plus R, and usually Ck is is much smaller than N. So we will be exploiting the sparsity for the problems that I'll be describing later on in the talk. And another approach that also will be looked at is how we can achieve cheaper relaxations. And these types of cheaper relaxations, they are based on the relaxation of the sum of squares polynomials. Amir Ali and Ghaddar, in their paper in 2013, they proposed the following SDD polynomial problem. So a polynomial can be said, or a polynomial is said to be an SDD or scaled diagonally dominant if it can be written in the following form. And I will show you next how it's written as. So instead of using K of R, we will be using S of R, where S of R is in the following form, where we have like scaled diagonally dominant SOS, And here, scale denominant SOS of degree R minus degree of G. And these SDSOSs can be written as a second order program. And it's exactly based on, and if you see it in the previous talk, so if you take each 2 by 2 principal minors of the STP matrix and say that this is an STP, which would lead to a second order cone condition, and then in this case, we will have this type of relaxation that we're ending up with. So instead of having one now big STP, you will take every 2 by 2 principal minor, say that this is an STP. However, this is a second order cone condition, and this would lead to much more type of constraints in terms of second order cone constraints. However, much better in terms of solution time. So how we can write that? Again, we have the same polynomials. However, these are instead of SOS, they are SDD. And these would be forming the SOCP constraints because we will have an SOCP condition over multiple SOCP condition over each and every one of them. Okay. These are computationally easier to solve. However, replacing the sum of squares polynomials by SDSOS, in this case, we have a problem because it does not guarantee any convergence. So we no longer have, as we increase the hierarchy level in terms of R, we are converging to the optimal solution. We have a slightly different hierarchy that we proposed. It's a bit more expensive, but based on SDD that allows us to prove this convergence. However, for practicality and for the purpose of the ACOPF, it's a bit expensive. So I'll be talking about the performance of this SDD type of approach without any modification, and unfortunately, we don't have any proof of convergence. So in terms of things that we have done, so we looked at sparsity, we looked at conic relaxations that are based on SOCP. The next step is how we can apply this to the optimal power flow problem. And why are we interested in the optimal power flow problem? We are interested in this problem because it's challenging. And like many real-world applications that are network-based, there are non-convexity in the models and the dynamics of the model. Like in the water networks, for example, we have friction head loss. Here in this case, we have the AC power flow limitations. We have also non-convexity in terms of the objective function. In most cases, we have combination of discrete and continuous variables like unit commitment plus ACOPF, valve placement plus the valve setting problem. And we have uncertainty in the parameters like demand, prices, and energy supply, for example. However, what do we have in these networks, like the energy network, the water network as well, is that the problem is very structured in terms of the constraints, the decision variables, and the pattern in terms of constructing the graph. We have a lot of sparsity. And in terms of uncertainty, we have samples of realization of these uncertainty parameters that we can model and we can achieve. So although the optimal solution for these problems are hard to solve, however, they are in high demand. And as you've seen, like in practice, from a practical point of view, just providing an improvement, a slight improvement in terms of the optimal solution can lead to billions of dollars of savings for utility companies, for example. So for the optimal power flow, what we've looked at is different things. What we've looked at is the formulation. The optimal power flow has really like a wide range of formulations, and some include the angle or the polar formulation, some include the complex formulation, there's the rectangular formulation. So there's different ways of formulating the model. We've looked at that. We've also looked at valid inequalities that are particular to the ACOPF. We've looked at sparsity, which is something that we'll be talking about. And we've also looked at interior point methods that are specialized, like SDP interior point methods that are specialized for the ACOPF, and how we can solve the SDP relaxation more efficiently from an interior point method point of view. We looked also at uncertainty and how we can use uncertainty from a polynomial optimization framework, and the development of new hierarchies and new conic relaxations for these problems. So today I'll be just focusing on the sparsity, on the uncertainty, and however, we have papers that are published for the other areas. So for the ACO optimal power flow, I will not go into the details again of the discussion since Miguel again introduced this problem really very nicely. Again, we are here trying to determine the optimal operating point of the electric power generation system in terms of trying to determine the power generated as well as the voltages, subject to a set of constraints related to the demand, related to the power flow constraints, as well as the bound limitations on the voltage as well as the power being generated. The problem is very challenging because it is non-convex, so we have very highly nonlinear equations in terms of the power flow equations, and also because of the scalability of the problems, like we would like to tackle large-scale optimal power flow problems. The work in terms of optimal power flow started to gain a lot of attention due to the work of Lavey and Lowe, where they showed the strength of the STP relaxation, and they show under some conditions that it can provide globally optimal solutions for these problems. And since then, a lot of work followed. There has been also some work done on polynomial optimization problems and how it can tackle such a problem. So we will be modeling this problem as a graph. Again, the nodes are the buses, and a subset of these nodes will be the generators. Also, there are branches connecting these nodes with each other. And some of these branches, a subset of these branches will have power flow limitations. The scalability of the problem makes it difficult in addition to the nonlinearities, but also as well, some use cases or some practical applications involve uncertainty. And in this case, we'll be looking at uncertainty in the renewable energy supply. And also some of the problems involve discrete decisions. And two of the problems that Miguel described involve binary variables. And this makes the problem very difficult to solve. We've looked also at problems involving discrete decision in terms of transmission network planning. And these problems become really difficult just by introducing these discrete decisions. We will be following a very similar notation to the Lavey-Lowe type of formulation that they used for the optimal power flow. So again, I said we have the buses, we have the generators, the branches, and a subset of these branches have power flow limitations. We have some bus parameters related to bounds on the active and reactive power, as well as some active and reactive load parameters, in addition to voltage limitations. We have the admittance matrix, Y, and we have some branch parameters as well that we will be looking at. The problem formulation we'll be looking at, it will be in matrix format. So we will be just formulating it slightly differently. So we will be following the matrix type of notation in terms of formulation. And for that, we will be defining these additional parameters. We will be formulating the problem using the X decision variable, where the X decision variable is the vector of real voltages as well as imaginary voltages. So if we have n buses, the X decision variable will be of size 2n because it's twice the number of buses, one for like a part for the real and a part for the imaginary. We are minimizing the cost of power being generated. We have the active and reactive power constraints in terms of bounds, the voltage bounds, as well as the power flow limitations. So given this problem, and because we're only formulating it in terms of voltages, we have a degree 4 polynomial optimization problem. And the degree 4 polynomial optimization problem is very difficult, even for very small instances. So instead, people looked at the degree 2 formulation, and for that, you would define a new variable, PGK, and this is the power being generated, the active power being generated, in addition to PLM and QLM. So you define them here in terms of the objective function, as well as here in the power flow limitation constraint. And then you add a set of equalities to indicate the value of these variables. Now, although we added a set of equalities, however, they are relatively very small because the number of generators is much smaller than the number of buses, and the number of branches with power flow limitations is also much lower than the number of edges. And also we have a sparse network. So usually these optimal power flow networks are pretty sparse. So going with this formulation, If we apply Lasserre's hierarchy, the SOS hierarchy of the first level, which is R setting it equals to 2, then it's exactly the conic dual of Laveyan law. Okay, and we have a proof of that, which means that if you even increase the hierarchy one step up, you will be either achieving the same or better bounds for this problem and eventually converging to the optimal solution. What we were able also to show is that for the optimal power flow problem, if we use the SDT hierarchy, which is the hierarchy of second order cone, we were able to show that this is exactly the conic dual of the problem proposed by Lowe and co-authors in 2013. So again, we were able to capture the first level of the hierarchy because the problem is exactly the same and as we increase in terms of R, we are able to improve in terms of the bounds. So here in terms of the STP bound and here in terms of the SOCP bound. What we can do also a step further is look at the sparsity, and the sparsity mostly is dictated by the admittance matrix. And if you take a look at the sparsity, we see that, for example, this is one example of the 39 buses. If we exploit the sparsity of the problem, and then the following two matrices, the one on top is the STP relaxation constraint matrix A, you can see that the number of columns is around 7,000. It's actually 7,114. While in the one that we exploit sparsity, the constraint matrix of the STP relaxation is around 2,500. Okay. So these are the same problem, the 39 buses, one without exploiting sparsity and one with exploiting sparsity. The maximum size of the STP matrix for the first one is 78 because we have 39 buses, so it's 2 times n, which is 78, while the size of the STP matrix, the maximum size of the STP matrix of the sparse version is 18, so it's much smaller. We end up here with much more STP blocks, 103 versus 95, but the CPU time is reduced to 0.3 seconds for this one. So there is an advantage of exploiting sparsity, and we would like to have that and exploit that in our problem. What we also do in terms of the clique extension is we keep the cliques of size 2, but we transform them instead of having them as an STP. We transform them into an SOCP, and we try to merge the cliques of value 3 and higher. Okay, so cliques of dimension 3 and higher, we merge them. However, the ones of size 2, we keep them because we transform them into an SOCP constraint. In terms of test results on these problems, we have the following. So this is the SDD. This is the STP, but without exploiting any sparsity. And this is the one with exploiting sparsity. And we have the gap as well as the running times. And you can see in terms of SDP without exploiting any sparsity, there's no hope of targeting large instances because like the SDP relaxation is too big, while the SDT and the sparse one, they are really good in terms of computation time. One struggles in terms of gap, like the SDT2 struggles in terms of gap, and you can see here for the largest instances, we have a bit of a gap. However, here we don't have a gap, like the gap, the gap is a bit smaller, but the computational time becomes a bit bigger. What we're looking at is at the SDD or the SOCP-based relaxation is reducing the dimension even further, because right now what we did is we didn't take all of the possible monomials to form the SOCP relaxation. We only took the monomials that are appearing in terms of the constraints. So if branches or if nodes, are connected with each other, then this monomial would appear in the SOCP relaxation. If two nodes are not connected with any branch or any edge, this means that we will not be using these in our SOCP formulation. So we exploited sparsity in the SOCP. So the next step we're looking at is trying to get one level up in terms of the hierarchy of the SOCP without incurring the number and the sizes of the SOCP that is exploding a bit in terms of computational time and memory. So the next step that we're looking at here is how can we solve SDD4 with limiting the number of SOCP constraints to be able to tackle this problem and get better bounds for this one as well. So that's in terms of conic relaxations for the optimal power flow problem. The next part that I want to spend time on is talking about our current work on exploiting polynomial optimization for the ACOPF, but including the uncertainty aspect there. So this is the main thing that I'll be talking about next. How can we develop methodologies to handle uncertainty and apply it to the OPF problems? We're also working in parallel on different types of conic relaxations for the mixed integer version of the ACOPF. And as I said there, we're looking at transmission expansion network planning. So that's a problem that we looked at, and it has the ACOPF as a sub-problem component, in addition to binary variables related to the expansion plan of the transmission network. So in terms of uncertainty, we will be looking at demand uncertainty in terms of forecasts, forecasts that are not being very accurate, and renewable uncertainty in terms of energy penetration. We'll be using an adjustable robust optimization framework for QCQP, and we'll be focusing on ellipsoidal uncertainty in this case. So let's consider again the optimal power flow problem, but now I will formulate it in the following general framework, just because it will make the notation a bit easier. So again, here we have we are minimizing the cost of power generated, subject to a set of bound constraints that are of the following form, and here are the non-convex equalities and inequalities that represent the power flow limitations, as well as some demand constraints on the problem. So this problem is exactly the same exactly the same as the one I presented before. We can notice here that the problem has two types of variables. We have the control variables that are Y, and here Y would represent the active powers on PV buses. And these are usually set by the operators, and they would like to know these control variables to set the system. And then we have the state variables, which are represented here by X. And these are the voltages in rectangular form. And these are dictated by the system. And mostly in our case for the ACOPF, they are coming from the physical constraints of the power flow limitations. In this case, here still the parameters are all deterministic. We assume that the demand forecasts are really are well known in advance and they are accurate, and renewable energy resources are like not intermittent in some sense, like whatever energy you're inputting, you're getting at the end as an output. However, that's not the case in practice, right? Like usually demand forecasts are inaccurate, and renewable energy resources like wind and solar are not exact in terms of the power that they generate at a given point in time. So we will be considering the uncertainty in power demand and generation. And this uncertainty zeta here, we will be denoting it as zeta, belongs to the ellipsoidal uncertainty set omega. And in this case, we will be using the ellipsoidal uncertainty set omega. It has some nice practical implications on this problem, but also from a theoretical point of view, we'll be using it when I show you some theoretical results later on. So now our problem is still like the same objective in terms of minimizing power generated cost. But now for the inequality and equality constraints, the non-convex equality and inequality constraint, we have this additional term zeta. And now instead of having m of these for each one of them, for each realization of this uncertainty, we will be looking at these following inequality and inequality constraints. So in some sense, we will be having infinitely many inequality and equality constraints that are quadratic in X. Notice that they are additive in zeta. So in terms of the uncertainty, they are just additive in zeta, but they are quadratic in our state variable. Now, in terms of quadratic inequalities, we know how to deal with that. Like they are still difficult, but we know how to deal with them. The problem becomes here with the equalities. In an adjustable robust optimization framework, dealing with these equalities is not trivial. And what typically is done in practice is that either this zeta is removed, which means that they only try to satisfy the equalities for the nominal case, so we don't have uncertainty being present here, or they try to eliminate these equalities by replacing x everywhere else in the problem using these equalities. However, in our case, we don't have a closed form solution that allows us to do that. So we cannot represent x as a function of zeta and y and replace it everywhere else. So what I'll be talking about next is how can we deal with these robust equalities in our problem, and what ways allow us to do that efficiently. So as I said, like we don't have, since like our equalities are quadratic in x, we don't have a closed form equation that allows us to substitute x in the other quadratic inequalities. However, for a second, let's assume I can do that. For a second, let's assume x can be written as a function of zeta and y, and also a little bit, something a bit nicer, that we can write it in linear form. Okay, so let's assume just for a second that we have this linear equalities. So now we have the following linear equality. So x is a linear function of y and zeta, which is the uncertainty. We are able now to replace x in these quadratic inequalities and eliminate x, so eliminate our state variable. So we'll end up with a new formulation, which will be a robust optimization problem that's only a function of y and zeta. So if we do that, let's do that. So x is in the following form. So this is the equality denoted in red. We replaced it here, the x transpose and the x, so it becomes of the following form. And now, instead of having x and y and zeta, we only have two variables, which are the control variables as well as the uncertainty variables. Now, we still have infinitely many inequality constraints because for each realization of the uncertainty, we need to satisfy these quadratic inequalities. The next step is we want to try to eliminate zeta. And for that, I will be combining the terms here in terms of the function or the degree of zeta. Okay, so I'll be first having the quadratic terms of zeta, then the linear terms of zeta, and then finally the terms that are not dependent on zeta. Let's write that here next. So I just rewrote the previous problem. It's exactly the same. I just rewrote it to have here the quadratic terms of in terms of zeta, the linear ones, and the ones that are not dependent on zeta. And now from what we noticed here is that this inequality is quadratic in zeta, and we have our ellipsoidal uncertainty is also quadratic in zeta. And that provides us with a nice theoretical result that we can use, which is based on the S-lemma. So the S-lemma allows us to rewrite or reformulate this problem exactly in the following form. So now we're replacing this infinitely many quadratic constraints by J STP convex constraints. So now we have still the same objective function, the same convex constraint here, like related to the bounds. But now, instead of these quadratic inequalities related to zeta and y, we end up with STP constraints and these equality non-convex constraints that I'll also talk about later on. Our problem now is only a function of y, and we have some auxiliary terms here, lambda j and gamma j, but they are linear and we know how to deal with them. And we can notice here that this STP constraint is dependent only on the size of AJ. So it's dependent only on the size of the quadratic terms in terms of the uncertainty set. So if our uncertainty is pretty small, so we don't have a lot of uncertainty terms, this STP constraint can be relatively small, which means that the size of STP is not the size of the full system. It's only based on the size of the uncertainty, and that can be really tractable and small to work with. We still have to deal with this non-convex constraint, but at least we went from infinitely many quadratic inequalities to quadratic convex tractable STP or conic constraints related to the STP, and these are for all J in the following set. So again, there's still one point that we need to discuss, which is how can I come up with these linear equalities that relate x to y and zeta? So that's still the missing part. If we have that, we will be using this part using an affine piecewise functions. So if we use piecewise-affine functions to come up with this component, let's assume we have done that. If we have done that, the algorithm will be as follows. So we will have a linear equality relating x with y and zeta. You will substitute x with these equalities and end up with a quadratic robust optimization problem. Then you will be using the S lemma to eliminate the zeta, which are the uncertainty variables, and end up with an SDP problem in Y and with some non-convex quadratic equalities. Now, solving the SDP with quadratic equalities, we deal with that using alternating projection approach. So that's how we deal with that. And we end up, in this case, with a robust control solution that is robust to the piecewise-affine approximation. So if we have the piecewise-affine approximation, all of these steps are exact. The only thing that we approximated was approximating this quadratic equality by using piecewise-affine functions. Everything that follows is pretty exact. Once we have that, we will check the feasibility of the control variable y. And if this is feasible for the adjustable robust problem, then we can end up with a certificate of either feasibility or infeasibility. So how do we come up with this piecewise-affine function? What we'll be doing is, since our quadratic equalities are only quadratic in terms of the state variable x, we will partition the feasible set x into subsets S1 through Sj. We will apply the algorithm that I talked about in the previous slide. We will apply it to these subsets. So for each subset Sk, we will be applying that algorithm and trying to find a robust feasible control solution. To be able to come up with the affine approximation, we will be using the Taylor series. So we will be starting with an x hat in the center of Sk. And usually what we would do is we start with a nominal solution of the problem. Then we linearize these equality constraints using Taylor series, and it has the following form. So we end up with a linear term in terms going from the quadratic term of x to a linear term of x, which means now we have x as a linear function of y and zeta. Now we choose the best robust control solution over all these subsets S1 through Sj, and we do some basic feasibility checks using some nominal power flow equalities. So with that, we can end up with a robust control feasible solution to the AC optimal power flow problem. The next part is I would like to talk about some computational results. We applied this technique or this algorithm to small instances of optimal power flow problems as well as medium instances. We used the math power instances and we ranged from 3 buses up to 118 buses. The uncertainty sets on the loads ranged differently for different instances. Some instances, the small ones, we were able to achieve a robust feasible solution for even bigger uncertainty sets. And sometimes, for example, for the 5 buses, we only were able to achieve for a 10% in terms of the variation of the loads. This is the nominal lower bound, which is found by the SDP relaxation. And this is the upper bound, which is the feasible solution, the robust feasible solution that we obtained from after our algorithm. For 9 buses, we were able also to go to high level of uncertainties, also for 14 buses. For 30, 39, up to 118, we were able, the uncertainty ranged between instances between 1 to 5% up to 20%. Okay, and under some conditions, sometimes our results were non-conclusive, so we're not able to prove feasibility or infeasibility of the problem. Here in this case, we had some numerical problems with MOSEC, so that's why we don't have results for these ones. But in general, what we found is that the adjustable robust optimization approach worked really well for small instances and medium instances of the ACOPF. And as well, we were able to show for medium level of uncertainty some interesting results in terms of the feasible solutions of the robust feasible solution for these problems. So in terms of this talk, what we have done is we try to use new conic relaxations to solve large-scale deterministic problems for the optimal power flow problem. And then for the case where we had uncertainty, we were able to solve small and medium-scale problems, find the controlled solution in very small amount of time, and use low to moderate levels of uncertainty to this problem. Now, although I presented this adjustable robust optimization approach for the ACOPF, however, it's applied for general polynomial optimization problems. The only thing that you need is to keep the ellipsoidal uncertainty in this case, and to have the equalities, like the y and the x, being like separable in terms of the equalities. Otherwise, you can have a general nonlinear equality or polynomial equality, and the inequalities need to be, in this case, quadratic, just to have the problem being tractable there. And with that, I will conclude my talk. What we're looking at next in terms of ideas is trying to combine different conic relaxations and different sparsity patterns for the deterministic problem, and also trying to incorporate that for the problems with the uncertainty. So trying to see if we can exploit the structure, because so far for the uncertainty, we didn't exploit any structure. So how can we exploit the structure in the uncertainty, and how can we solve larger cases in terms of scale for these problems? That's in terms of the next steps. And with that, I'll thank you all very much. And thank you again for Wala and Henry for organizing such a nice seminar.
Thank you so much, Bissan, for the nice talk. Are there any questions or comments to Bissan? Miguel, please.
I have a question. Thank you, Bissan. Very nice. Very nice. I was especially appreciating the bit about the uncertainty, because, as I mentioned, that's highly relevant. I'm going to pick on one of the details that you mentioned there, which is that you said that you use an alternating projections approach. So the question is basically in two parts. The first part is, can you give a little bit more detail on how you do that, or what, how that works, and how is the convergence of that? Because sometimes that can be very slow.
Yeah, exactly. So in terms of details, so I can show you exactly the details in the paper. So we have an archive paper on archive that talks about that in details. But in terms of general idea, so we remove these equalities. So maybe let me share my screen again. Yeah, so we first start by solving the problem, but without any of these equalities. And then we get a solution. Then we try to check the feasibility of that solution and project it back to these equalities. And if it's not feasible, we continue iterating until we try to converge. In terms of convergence, yes, I agree with you. And I think we have a couple of instances that didn't converge. I don't recall which ones, but we had some issues in terms of convergence of these techniques. But it was very dependent, I would say, on the S values here, the S regions, sorry. Because if you take them really small enough, in some sense, you would have your affine approximation very close to it being exact. And then the region is also very small, so you can work with them really nicely. So, and if we start from the nominal solution also of the original problem, we didn't have a lot of issues for the optimal power flow problem, but I expect, yes, we might have some convergence issues with other instances. But since we have the nominal solution in this case, we were able to really stay close to that and achieve good results.
Good, thanks. Yeah, it's important to use the fact that we know the problem, we understand the dynamics, and that can be brought to bear to improve these things. So that's good. That's good. Thank you.
You're welcome. Thanks, Miguel.
Thank you, Miguel. Thanks, Bissan. Any more questions or comments to Bissan, please? Well, if not, I have one comment that's related also to Miguel's comment about alternating projection things. So if you can go back to that slide, Bissan.
Yes.
So I have two comments here. First, sometimes other projection-based methods perform better than alternating projections. If you look for feasibility in terms of conversions, perhaps Douglas-Rashford sometimes do better in the sense that it has two sequences and one of them would go actually closer to the solution. The other thing is that if you're using an affine approximation for these sets, there is also what's called the Gerhardt-Cauchy acceleration for alternating projections. And there's a very recent paper, so it's basically for linear subspaces, but there's a very recent paper that adapts this acceleration to affine subspaces by Matt Tam. I can send you the paper. It's a very nice paper that like you can accelerate this so you can get closer and faster to a feasible solution.
Thank you. Yeah, well, it would be interesting because this is like a very recent work. So in terms of improvements, I think there's a lot to be done. And I would appreciate if you can send me the reference.
I will send, it's a short one, so it's nice, but it has a very nice adaptation. So it gets you closer to, because always you get a linear rate, but indeed, as Miguel said, it could be very slow. Sometimes if the angles between these subspaces is very tiny, that the alternating projection does not do as well. Like maybe you better in this case consider something like Douglas-Rashford because it has a very like non-monotonic behavior that goes better. So I'll send you both papers actually.
I would appreciate that. Thank you. Thanks.
Thank you, Bissan. Very nice talk. Any more questions or comments to Bissan? Henry, you are muted.
So maybe I'll stop the recording if I can figure it out.